Welcome back, everyone. We are continuing these presentations given by the early career scientists volunteering here at the COP26 Cryosphere Pavilion. This is the very last presentation, and it is my great joy to welcome Maxence Menton, who is a PhD student at Vrije University in Amsterdam. Take it away, Max.
Hello everyone, thank you for being here. So my name is Maxence Menton, I'm PhD at the Vrije University of Amsterdam. And I would like to present you today different perspective about the ice, the land ice, according to my previous experiences. And in the background here is the Glacier of Argentière in France, nearby the Mont Blanc. A picture taken the last summer. And yeah, it's a really beautiful place. That's nearby where I come from, and I guess it's why I get interested in glaciology. So I will talk about the different land ice that we have on Earth, which includes the mountain glaciers and the two ice sheets, the Greenland and Antarctica. The numbers shown here are the potential contribution to sea level rise if they completely melt away. However, I would like to mention that the mountain glaciers, even though they have a lower impact in terms of sea level rise, they have a tremendous importance for freshwater resources. And during this presentation, I will talk about these three different elements with three different point of views. I will start with the mountain glaciers with a satellite observation, and then I will talk about Greenland with my experience on the field, and then I will present briefly my PhD project about modeling the Antarctica with paleo records. So to start with, I would like everything I will talk about the mountain glaciers is based on this study. I had the chance to work with Romain Gonnet and Etienne Berthier, first and third author of this paper. And yeah, it's been published this spring. And it's, for me, a very outstanding paper, which I think everyone should be aware of. So the key results, straight to the point, is that the glaciers worldwide are losing mass of 267 gigatons per year in average between 2000 and 2019. And most importantly, this melt is accelerating over the last 2 decades, as you can see on the figure on the left. But why this paper is really outstanding, if you look at the previous literature, which did similar analysis, the last IPCC report from 2018, they estimated this mass loss of 278 gigatons per year with an uncertainty of about 81%. Zemp and others did a similar work, which enabled to have this result in the IPCC report 2 years before, which was 335 gigatons per year with an uncertainty of about 40%. And in this paper, they succeed to tremendously reduce the uncertainty of 6%. So it's a huge advance in this field of research, and it's those kind of results which really help us to think that we still have a lot to learn. We can still do a lot in climate research, and it's really worth it to keep working on this field. If you look at the map, that's what it looks like in average for the two last decades. So the circles represent how big the mass loss was during these last 2 decades. So, and the fringe just under the color in from yellow to red represents how fast the elevation changes for every year between 2000 and 2019. So what we see is that, for instance, in Greenland, in New Zealand, um, this melt is accelerating a lot, even though the glaciers are very small compared to the other ones. Similarly, we can see that Alaska is a big contributor in terms of loss um, of mass. It's actually the biggest one in terms of mountains, glaciers. And we so the picture I show in the first slide is from the Alps, and you see that they are melting really fast as well, but they are also very small compared to the other glaciers of the world. So how did they succeed to reduce so much the uncertainty? So they included more than 200,000 glaciers, and they processed a million Aster images, which is images given from Aster instrument, which is on a satellite. And they developed a method which is called Asterix, which means Aster monitoring of ice towards extinction. And they used independent measurements to validate the results, which enable to reduce the uncertainties. That's it for the mountain glaciers. So we'll move on to the Greenland ice sheet. And I want to start with the fact that the Greenland ice sheet is losing mass as well during the last 2 decades. So it means that it's melting more every summer than it's winning mass during the winters. I would like you to pay attention to the year 2012 and 2019. 2012 now is the record melt, and almost at the end you have 2019, which is the year I was on Greenland on the field, which almost broke the record for from 2012. So I was on the field with Jason Box, Masashi Niwano, and Maurice Tingelen. We were over there at the southern tip of Greenland. So what we do there, we basically install poles. So we drill in the ice. We implement a pole. We measure how much is above the ice, and then we come the next year and measure how much is actually still above the ice. So yeah, so you can imagine that when we installed the pole, the ice was until here, and when you come 1 year later, it's several meters lower. So when you multiply this height by the surface, you can imagine the volume of mass loss from Greenland. So here you can see Maurice and Jason measuring how much the pole is above the ice, and myself drilling to prepare to install the new one for the next year. And this year was the year 2019 was almost a record year in terms of melt from Greenland, because we had also heat waves which went through Europe, where we had all-time record of high temperature in Belgium, France, Netherlands, UK, Germany, Luxembourg, um, and these heat waves um, went then to Greenland, and when they were there, they triggered the high melt on the surface. So also when you're on the field, the melt is manifested as this, which means that you have surface melt and it creates sort of rivers, and the runoff can sometimes go through the ice, through what we call the moulin. And those areas, um, so it means that the water goes under the ice and it can accelerate the ice in terms of sliding. So if the ice is, so the friction between the ice and the land is lower because of the water under the ice. Other things that we can see on Greenland when we are on the field, on those pictures we can see many things. The first one is that the ice is actually dark. That was really shocking for me when I was there. because I was really expecting, I grew up in the Alps, so I know what it is to go skiing when you have fresh water from the night before and it's white, it's magical, and and I was expecting something similar when I was going to Greenland. But in fact, a lot of areas were actually black or gray. And this is due from algae developing on Greenland because the temperature is high enough, and or black carbones or aerosols depositing on the ice, which can come from forest fires, for instance. And this triggers the albedo feedback that you certainly know about, which is when it's getting darker, it's absorbing more heat from the sunlight, which means it's getting even darker. So more heat, darker, and it's just melting away. And the second thing here, which is quite interesting, is that we see a collapse of the ice before the ice cliff front. And we guess that this was triggered by what I showed before, a moulin, where the ice was going through. At one point, there was so much water under that it just collapsed. The third thing is that about 10 years ago, this glacier was there. And you can imagine the scale because Maurice is on the picture. And you can imagine how far the glacier was just 10 years ago. Then I will move on to Antarctica. And once again, I would like to start by mentioning the fact that it is also losing mass. Even though in some areas it is indeed winning a little bit of mass because of increase of snowfalls, in average, if we take everything into account, the losses and the win, um, it is losing mass. On the western part, you see it's getting really dark. It is where the Thwaites and the Pine Island glaciers are, and those glaciers are above a continent which is lying under the ocean and is getting deeper and deeper, which could trigger a marine acid instability. My PhD is about understanding how the Antarctic ice sheet evolved in the last interglacial. But what is the last interglacial? The last interglacial is this period. Because here on the graphic, you can see the evolution of CO2 in the atmosphere and the temperature in the atmosphere during the last 800,000 years. And you can see that it's oscillating between interglacial and glacial states. And we are on the left side during the Holocene, so the current climate, and we see how much we are putting CO2 in the atmosphere, and we can see that it never happened for at least 2 million years, in fact, and we see that it's way further than this graphic. And the last interglacial is interesting because we can see that in this graph, the temperature is actually higher than the current climate, but not now anymore because we already have 1 degree of warming, and it is about the climate that we had at this time. If you connect this to the sea level, we can see that so the MIS5 is another way to call the last interglacial, and you can see that at this time the sea level was 6 to 9 meters above the current sea level. And it's quite interesting because the global warming was about 1 degree warmer, but for 10,000 years. And we can see here from the geological records that it makes a huge difference if we stay in the same climate for a long time. And if you go even further on time, you can see that with higher temperature in the atmosphere, we have also higher sea level rise. But let's stick to the last interglacial. In the last interglacial, according to this study, the Antarctica was the main contributor to the sea level rise. So AIS is Antarctic ice sheet, GRIS is Greenland ice sheet, and you can see the thermal expansion and mountain glaciers are actually a very small part of it. So my PhD is about what Ellen presented earlier, coupling an Earth system model with an ice sheet model. and comparing those results with the geological records from which we have the results I just presented earlier. Because we have the order of magnitude, but we don't know exactly which processes trigger this melt from Antarctica, how fast did it melt, and most importantly, if it's likely or not to happen in the next centuries or millennia. So to conclude, I would like to conclude with the fact that we know that all of them are melting away for at least 2 decades. And this caused water shortage, sea level rise, etc. A lot of very sad stories. And this is up to us. We can still choose how much will melt in the future and how much the consequences will have. But outside the consequences, I would like to remind that saving ice is also saving beauty because, for instance, you see on the right hand side, it's myself, about 7 months old, in the arms of my mother in front of the glaciers nearby where I come from, nearby the Mont Blanc. And I could not take this picture anymore with my children. On the left, it's where I live now in Amsterdam. It's far from the glaciers, it's far from Antarctica, it's far from Greenland, but still is directly threatened by the sea level rise. And it is a beautiful place. So now the question is if we should be motivated by fear or beauty and love, but it's up to us, but we have to do it. Thank you very much. Any questions, please? Yeah.
Thanks for the
Oh, wait.
presentation.
Wait.
So this might be a slightly technical question here at this
All right.
point, but since there has been talk here in this pavilion about it before as well, about the marine ice cliff instability, so this mechanism where more and more calving happens as we're retreating the ice sheet. Are you going to include this mechanism in your model experiments or not?
Yeah, really good question. Yes, because I think there is still more study that needs to be done to know if this mechanism is relevant in terms of processes to better understand how the Antarctic will evolve. So I think we still don't have enough constraint on whether we should exclude it or include it. So yes, I will include this, and I will also come back to what Ellen presented earlier. So she presented that according to her results, the oceanic forcing is the main driver rather than the atmospheric forcing. And that's what I've been done during my first year. I've been improving the interaction between the ice and the ocean by implementing the PICO module, which is more sophisticated than what I was before in the model. Any other questions? Yeah.
If you and Helen would go with a joint message, how would you combine this? Is Helen here? How would you combine your findings in order to deliver a clear message, let's say, to the policymakers, the negotiators here?
I think that the message is already clear from the geological records. Even though the uncertainties are quite big, we cannot afford to have several meters of sea level rise. And we know that it was the case from geological records. From the modeling perspective, it's more understanding about how fast it will happen. But we already know that the threat is here if we stay in this climate or we make it even worse. So the message is very clear in the sense that we will have consequences, but the magnitude of it is up to us. So yeah, that's it, I think.
Hello. So this gentleman here kind of read my mind because I wanted to ask something like that, but maybe I will be like a little bit more precise in as a researcher. Like we know the impact is clear, but there's any opportunities inside, for example, your university or any other institution that you've been sharing this information for actually bring this into some policymakers, like not just as this is the research, but okay, this is the research, this is the advice, so you should consider this for applying it in this manner. So I would like to know about your experience in that, if it's any opportunity or availability actually for research to materialize all this data into something that can be actually put into society and the policy making for control all these impacts.
Yeah, thank you very much for your question, because um, I'm only an early career scientist, and that's actually exactly the question I asked to many scientists I met here. So I actually don't have the answer, but what is sure is that I try to do my best. The proof is I'm here, and last week I was here, but with another organization as well, which is a Climate Risk, which is amazing as well. So I think indeed that scientists need to make the bridge way more between the society and the result that they have. And the present the publication that I presented from the glaciers mountain melting, they did a great job, because we hear about this publication for at least 2 weeks, and maybe that's also something I learned during this COP, is that if you satisfy yourself by doing the research but you don't reach the people, you have to reach the media, but they don't always come to you. So it's maybe a work that we have to do, us as researchers, is to actually reach the people, um, to bring the messages. So it's to bring the information, but then how to make this information relevant for the society? It's actually, I think it's actually a whole research field in itself, um, in the sense that 1 meters of sea level rise, the impact will be completely different from if it is in Netherlands or in Bangladesh or um, Norway or Brazil. So the consequences will be different, and the quantifying this risk is a whole skill, I think, in itself. So that's certainly something I could look into, but it's definitely like going further than what I am supposed to do.
May I just add on this and maybe condense it a little bit? But first, I think communicating always includes two sides. And my view is, or my experience is, that the scientists do their job, but you need also somebody to listen.
Mhm.
I think if we have the audience that listens to us, we are quite good in communicating, at least most of us. So, and there is no answer. I do not know how to bring the people to listen to us, but just if maybe this sounds a little bit silly or like a joke, but shouldn't there be a Sharm el Sheikh COP27 agreement that replaces the Paris Agreement, and it would say not stopping at 1.5 but getting back as soon as possible to 0.5? That is the message I get from you, from the two of you, and from all the others that do these long-term ice sheet studies.
Yes, definitely we need to go back if possible. I think the presentation from your Jerry this morning was really good, because um, he sort of balanced what we can do and what we should do, and he really mentioned the fact that we have different aspects in the world to take into considerations, which makes it really hard, and 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 yeah, from this data we know that we cannot stay in this climate for thousands of years, otherwise the sea level will rise for a long time, and we will have other consequences as well. Um, so yeah, I mean, I think we do, all of us agree on the fact that we have to stay as low as possible, and we should not satisfy with the very small steps, but really all of us should do our best. Everyone, every time, all the time, um, and I think that's the only way to go, because you have to show the example. And sometimes I always take the example that when I went to Sweden, it was in 2018, 17. I went by train and buses, and everyone thought I was kind of crazy, um, because it takes way more time. It's way more expensive. And the year later, 1 year later, Greta came out, and all of a sudden, everyone understand why it makes sense to take the train and the bus rather than the plane. So I think showing the example is the right way to go. Then it, but it, yeah, it doesn't really answer your question about the next COP. Um, I think from this COP also I learned that I think science should have a way bigger place in the COP itself. Uh, as all of us know, it's really hard to get into the negotiations, to observe only the negotiations, not all of them. And I'm not sure how much the science is inside. So that's also maybe something that us scientists can work on together, because there is also the peatland pavilion here, there is a science pavilion here. So there is certainly a lot of consortium that we can bring to the policymakers. But I mean, that's more or less what that it is what the IPCC is doing. But maybe the IPCC should have a bigger place within the negotiation of the COP. Yeah.
Two comments really. Addressing your second one first, actually, Valerie was discussing the possibility of doing a science corner at the next COP potentially, where we have cryosphere, water, peatlands,
Hmm. Yeah.
oceans,
That would be
IPCC
great.
sort of all together. But in answer to Georg's question, really that would never take place at COP27, but the proper place for that, which some of you have heard me talk about, is in the second periodic review and the global stocktake. And those are the processes where that possibility can certainly be raised, because the Paris Agreement that's why those processes are included in the Paris Agreement. As the science evolves, the countries review the long-term temperature goal continually. And again, the out is long term. There was a decision to keep the current temperature goal, at least for now. But what do we mean by long term? Maybe long term requires a return below 1 degrees.
Hmm.
And then, of course, the global stocktake, which is to prevent. I'm blanking on the language, but it's a lot. The paraphrasing, to prevent absolutely negative impacts from anthropogenic climate change.
Thank you. Any other questions or comments? Right. Thank you very much. And this is done for the events of the Croatia Pavilion. I don't know if you, Pan, would like to conclude.
Yes, this does conclude events at the Cryosphere Pavilion at COP26, unless something really unusual happens, in which case we're happy to continue to host, because as I said at the beginning of the day today, it's rather unlikely that the COP will conclude as planned at 5 p.m. this afternoon. We will stop the clock and we'll see probably when 5 p.m. on November 12th occurs in COP world. So thank you so much to everyone who's been watching. Thank you to the Geneva and Stockholm hubs in particular, and to the early career scientists who've been volunteering at this pavilion. Also want to thank Heidi, who you've seen many times, and Amy, who is in the back there, who has been a wonderful attribute, and Nick, who has been managing. Yay. All of this very, very complex technology that has allowed us not only to bring the science into the COP, but bring it via live stream to folks who are watching and can watch this actually in coming years. So thank you so very much. And perhaps we'll see you next year in Sharm el Sheikh, Egypt. Bye.